When we're zooming along through the air, how do we know how fast we're going? Well, let's find out. Hi, I'm Grant and welcome to the 5th class in the instrumentation series. Today we're going to be taking a look at how we measure airspeed. We want to monitor our airspeed so we don't fly too slow and stall, or fly too fast and cause any damage to the structure of the aircraft. They're essential pieces of kit for the cockpit and you'll use them all the time, but thankfully they're quite simple to understand. Before we get into how we measure the speed we're going at, I'm going to first break down all the different speeds. When flying around, you won't use all of them, usually just indicate the airspeed and Mach number, but we'll see how they all interact with each other and basically form a base level of understanding of each of these different speeds before we get going. First, we get a reading from our instrument. How we do that, we'll talk about later, and this is the number on the dial. It's called the indicated airspeed because it's the airspeed that we have indicated to us. It is the most readily available piece of data we have on speed, so it is often the value we use when flying around, and we also use it for maneuver speeds like the speed for the best climb angle, or limiting speeds like flap extension speeds. If we have an older aircraft, the springs and mechanisms within the airspeed indicator start to wear and an error can start to form. For the aircraft to be legally certified, this error can't be too great, but a certain tolerance for accuracy will be allowed to account for older instruments. For example, if we know that we had an old airspeed indicator that always reads 2 knots faster than the real speed, we can do a quick subtraction of 2 knots from all display speeds to calibrate the instrument properly. This new airspeed is called the calibrated airspeed. In most aircraft, especially those using newer electronic devices for measuring speed, the difference is so small that in practice, indicated airspeed and calibrated airspeed are almost identical. At low speeds, the air we're flying through and the air we are measuring are the same. When we start to fly faster though, the air will start to compress in our airspeed probe. It's almost like a traffic jam on the motorway or something. One car brakes, holding up the one behind it, forcing it to brake, holding up the one behind it, and so on and so on. The effect sort of ripples back the way, so at one point you have perfectly free-flowing cars slowing down as they compress together. If we had 2 roads parallel to each other, the one with the traffic jam and the one with the free-flowing cars would see a big difference in the speed of those cars. This is the same sort of thing that's happening within the airspeed probe. The traffic jam occurs in the probe, meaning the reading from it is different to the free-flowing air we're actually flying through. This effect only happens above around 200 knots and above 10,000 feet, but the effect doesn't become significant until our true airspeed goes above 300 knots. If we correct for this compressibility effect, we can convert our calibrated airspeed into an equivalent airspeed. And that 300 knot value is something that you'll see on a CRP5 calculator, for example. You won't really apply corrections concerning compressibility until the true airspeed gets above 300 knots. Airspeed is measured using the density of the air. Just trust me on that for now, all will become clear soon as we dive deeper into this class. If we were to just use a constant value for density, like the ISA 1.225 kilograms per meter cubed, then our speed that is calculated using that density would start to become incorrect as the density changes as we climb in the atmosphere. So we must correct for the changing density to get a true airspeed. This correction can be quite significant. When flying at high altitudes, you can easily see a true airspeed that is double what we have indicated, and the other corrections have quite a small impact compared to this density correction, meaning that for most modern aircraft that have highly accurate instruments, the indicated airspeed, calibrated airspeed, and equivalent airspeed are often thought to be so close as to make no difference, whereas the true airspeed and the indicated airspeed difference is very significant. Mach number is our true airspeed as a proportion of the speed of sound. At Mach 1, you would be traveling at the speed of sound. If we were in a 737, for example, traveling at a typical cruise Mach number of 0.75, we would simply take the speed of sound, which is 340 meters per second or 661 knots, and multiply that speed of sound by 0.75 and see that our 737 is traveling through the air at 496 knots. This means that a flight, for example, that I did recently from Edinburgh to Gran Canaria, a distance of 1,760 nautical miles, should have taken me about 3.5 hours. So why did it take me 4 hours and 20 minutes whilst traveling at the speed of sound? Well, the speed of sound is only 661 knots when the temperature is about 20 degrees. So despite my Mach number being the same, the temperature at 37,000 feet was not 20 degrees. As the temperature reduces, so does the speed of sound. And when we fly at high altitudes, it gets colder, so we must calculate a new local speed of sound for where we are. And to do that calculation, we use this formula here. We've got 38.94 times the square root of the temperature with the temperature in Kelvin. So if you apply the temperature of an ice a day at 37,000 feet, let's say, well actually we'll write it down, let's just do this as a live example. So let's say at 37,000 feet, the temperature is going to be minus 57 degrees because we're above the tropopause, which is at 36,090 feet, and the temperature stops reducing above the tropopause, meaning that the temperature is minus 57 degrees C, and that is 216 Kelvin. So then if we plug that in to our local speed of sound calculation, I've done this obviously off screen, but we could see that the local speed of sound equals 572 knots. So if we then use that 572 value and we said that our Mach number was going to be 0.75, so 0.75 equals our true airspeed over 572, meaning that our true airspeed is going to be equal to 430 knots pretty much. We would then see that the time equals 4.1 hours, which is 4 hours and 6 minutes, which is a very significant difference. So the temperature makes a huge difference. And obviously this wasn't necessarily an ice a day when I did this flight, and this calculation doesn't consider any winds or route inefficiencies, but the principle remains the same. The higher up you are, the slower the same Mach number is, and this is because the local speed of sound reduces as it gets colder, and it gets colder as you get higher up in the atmosphere. All those speeds we just talked about are interlinked, but the details on how one changes when the other one does can be quite confusing. Say for instance we're flying at a constant indicated airspeed, then start to descend. What happens to the Mach number if we keep that constant indicated speed in the descent? You could work out what the density correction would be, get the TAS, and then figure out the local speed of sound, that it would likely increase, etc. But there's a much easier way. We just take 4 fingers or draw 4 lines like this, and remember the order as ECTM, or as I remembered it, Eat Chicken Tikka Masala. From left to right we have the equivalent airspeed, then we have the calibrated airspeed, which remember is essentially the same as the indicated airspeed apart from a very old aircraft. Then we have true airspeed and Mach number. And these 4 lines allow us to tell what happens to all other speeds in relation to the others. Let's use the example from before and say we were flying at constant indicated airspeed. Remember that the calibrated airspeed is essentially the same. And then we descended at that constant indicated airspeed. If our indicated airspeed is constant, then we can rotate all the lines so that the indicated airspeed is constant at all altitudes, aka a straight line. This is why sometimes it's easier just to use your fingers, because you can obviously rotate them a lot easier with reference to these lines. If we come down through all the altitudes at a constant indicated airspeed or calibrated airspeed, we can see that the Mach number starts to reduce. We can also see that the TAS decreases as we descend, which makes sense. The density correction that we must apply at higher altitudes eventually reduces to nothing when we are flying at the correct density for the instrument, making the TAS and the indicated airspeed the same. So you can see the relations already just by using 4 simple lines. You can also rotate the lines to make any speed remain constant for climbing and ascending, and see what happens to the other speeds. For example, quickly just using my fingers, if we were to climb at a constant Mach number, I'll switch my hand so I can actually rotate it, a Mach number, let's say this was the constant value and we're climbing up, we can see that all the other speeds decrease as we're climbing up if our Mach number remains constant, which is sort of what we were talking about before. So a nice little trick to figure out in questions if they say what happens when you climb or descend at a certain speed remaining constant. This is the tool to use to see what happens to the other speeds. Eat chicken tikka masala, and if you like, you could do chicken tikka masala, chicken, to remind you that calibrated airspeed and indicated airspeed are basically the same. Okay, so now we understand the different types of airspeed and how they are related. Let's see how we measure it. There's a formula we use that underlies how every type of instrument calculates the airspeed, which is the total pressure equals the static pressure plus the dynamic pressure, and the dynamic pressure is made up of a half rho for density and v squared. So this v squared element is sort of how we're deriving the speed from this formula. So basically what this formula is saying is that the total pressure is made up of a static component, that's what you're feeling all around you now, plus the dynamic pressure, which is the pressure you feel when you're traveling through the air, which is very noticeable when you're on a bike or something like that. So what we do for an airspeed indicator is we measure the total pressure, which is often called pitot pressure, and this is done through a pitot probe or a pitot tube, which is essentially a tube pointing out into the airflow, taking in air as we fly through it. Then we take away the static pressure, which is measured by a static port, like we've seen in previous classes. And this way we can find out what the dynamic pressure is, which is a good indicator of the speed. In a basic speed indicator, we feed static pressure into an airtight container, and then the pitot pressure goes into a capsule or a bellows. The bellows will only inflate and deflate according to the difference between the total pressure in the bellows and the static pressure in the surrounding case, and that difference is going to be the dynamic pressure. This dynamic pressure is mechanically converted into a speed value and movement of a needle on a dial. The problem with a basic airspeed indicator is the mechanical linkage will be calibrated to sea level ISA density. We've basically set a fixed value for density in this equation through the mechanism in the instrument. So as we fly higher with lower density, the reading for the indicated airspeed starts to differ from the true airspeed as the density reduces, making basic airspeed indicators unsuitable for high altitude flight, where the difference in densities would cause quite a large error, that error between true airspeed and indicated airspeed that we talked about before. The mechanical linkages will also start to wear and get old, which can lead to a fall in accuracy and a large error, making the calibrated airspeed different from the indicated airspeed and accurate flying quite difficult. To counteract this, in slightly more advanced and newer systems, you might see an EI electronic system to monitor the movement that I talked about in the class on altimeters as well. So in a more advanced airspeed indicator, all we need to do to measure the speed is have a total pressure value and a static pressure value. With a system using air data computers, we can take the pitot pressure and subtract the static pressure from the static ports. Then we can use that dynamic pressure to give an accurate value for indicated airspeed. And through using the data from the static ports, we can also get an accurate value for altitude. The computer will then have a database in it with density values for all the altitudes we're flying at, and this value for density can then be inserted into the equation for dynamic pressure. And therefore, a more accurate value for the true airspeed can be calculated depending on that new air density for that level that we're at. This can then be displayed on the primary flight display as an indicated airspeed on a speed tape, and we can also get good values for true airspeed and Mach number, as we'll see in the next slide, if you like. And if we apply wind, we can get values for ground speed as well. We normally have the indicated airspeed as the primary source rather than the true airspeed. And the reason for this is that not everyone has a fancy airspeed indicator. Some aircraft will still be using those basic airspeed indicators. So in order for air traffic control to control the flow of aircraft accurately, we all need to be flying using the same reference. So we all fly using the more basic reading of indicated airspeed when at low level. We basically all fly around with the knowledge of the indicated airspeed and the true airspeed having an error, but that error will be the same for all aircraft at that level. And it's basically we, in a complicated aircraft with a more advanced airspeed indicator, we basically accept that fault and reduce our accuracy down to the level of a basic airspeed indicator, but it doesn't matter because everybody's flying with the same error. When at high altitudes, we use Mach numbers to fly. This is to prevent the aircraft from creating accidental shock waves. For more information, check out my videos on supersonic flight in the POF series. So if we were flying at indicated airspeed and climb, for example, we can see that if we use the eat chicken tikka masala method, that if we're flying constant indicated airspeed and climb, the Mach number starts to increase. If it gets above Mach 1, then a shock wave can form, which is bad for several reasons. And if we climb at constant Mach numbers, we avoid this even if the true airspeed and indicated airspeed reduce as a result. It's quite hard to bend my wrist so that my thumb is straight at this angle, but hopefully you get the idea. If we fly around using Mach numbers and climbing and descending, it takes care of the true airspeed and the indicated airspeed. They're always going to be lower than the Mach number. The Mach number is dependent on the local speed of sound, and the local speed of sound varies with the temperature, and the formula 38.94 times the square root of temperature in Kelvin. So it would make sense that a Mach meter would have some sort of temperature sensor in it. In reality though, the two things we need for Mach number, TAS and local speed of sound, both vary with temperature. The local speed of sound obviously varies because of this equation, but the TAS varies with temperature because the changes in temperature will influence the density of the air, and the TAS is the indicated airspeed or the calibrated airspeed corrected for density changes. So if we're flying at a fixed Mach number, any temperature changes as we climb or descend wouldn't really matter because both things we are measuring are being influenced by the same temperature change. What this means is that the ratio between them remains unchanged, and we can think of Mach number as essentially the dynamic pressure divided by the static pressure, which is a strange thing to get your head around, having just told you that Mach number is only dependent on the temperature. But because both things are getting changed by the temperature, you can just mathematically reduce it to dynamic pressure over static pressure. This is the mathematical relationship that is used by Mach meters. Mach meters basically measure the dynamic pressure using the same method as an airspeed indicator, then measure the static pressure, and through clever mechanical gears and springs, etc., compare one reading to the other and generate a ratio between them, which is the Mach number. This is then translated into a rotating drum dial, I've called it. I don't know what you would call it, but it will then be housed within the normal airspeed indicator. You know, it's like all those numbers just roll by. Hopefully you get what I mean. In more modern air data computer-based airspeed systems, they'll use the same ratio of dynamic pressure gathered from a pitot tube and the static pressure gathered from the static ports. And then to compare the static pressure, we then use software to calculate the Mach number instead of mechanical linkages, which can then be displayed on the primary flight display, usually below the speed tape. Okay, to summarize then, we've got a few different types of speed. We've got the indicated airspeed. If you correct it for any errors in the instrumentation, you get the calibrated airspeed. It'll only really exist in older mechanical airspeed indicators. If we then correct for the compressibility effect, we get the equivalent airspeed. This is primarily used by sort of designers when thinking of the aerodynamics and the aerodynamic properties of aircraft. You don't really use equivalent airspeed all that much when you're flying. If you then correct again for the density error, because the instrument will be calibrated for a certain density, you're not always flying at that certain density. And if you look at this equation, you can see that the density plays a role. The dynamic pressure varies with density. So if you correct for a new density for the actual altitude you're at, then you get the true airspeed. The difference between indicated airspeed and true airspeed can be quite great because indicated airspeed, as I said, the instrument is set up for 1.225 kilograms per meter cubed, but you're actually flying with a density of 0.5 kilograms per meter cubed or something like that, then you're going to get very different values because this equation's not going to make sense, and therefore the result's warped. If we want to fly with Mach number, we do the true airspeed divided by the local speed of sound. Local speed of sound is 38.94 multiplied by the square root of the temperature in Kelvin. Yeah, that's pretty much it. Mach number is used at high levels because if you're climbing and descending with Mach numbers, the true airspeed and all the other speeds are always lower. Whereas if you were to fly with a constant indicated airspeed, for example, then you climb and descend, the Mach number might go up and down below Mach 1, which would cause shock waves. The Icha Kantika Masala method, very useful. Use your fingers or draw the lines to figure out what's happening to one speed when the other ones are held constant, essentially. The formula that is the fundamental principle behind airspeed indicators is that the total pressure measured by the pitot tube is the static pressure measured by the static ports plus the dynamic pressure. That's sort of the unknown value. It's referenced and related to the speed. So by measuring the dynamic pressure, we can get a value for the speed. In a basic airspeed indicator, we have the total pressure going into a bellows, static pressure going into the surrounds. The bellows will only inflate by the difference, which is going to be the dynamic pressure. It will be set up to have a set value for density, which makes it a bit unreliable when flying at high altitudes. So there will be a big difference between indicated airspeed and true airspeed. A method to correct that is to obviously use a much more modern, brand new bit of kit. You get the same sort of difference comparative reading to get a dynamic pressure, but then you can substitute in a value for density based on the altitude you're at, giving you a much more accurate value for true airspeed. But we often only fly around using indicated airspeed because there's going to be some people that might still be flying around using a bit of kit like this. So even if we've got the data readily available to us, we kind of have to correct to the lowest common denominator and all fly around on indicated airspeed at low levels. And at high levels, Mach number I already talked about. For a Mach meter, you can also think of the relationship of Mach number as the dynamic pressure over the static pressure. This is because the temperature changes that influence the local speed of sound also influence the TAS, because the TAS is affected by the density, and the density will also change with the temperature. The air expands and contracts, it becomes less dense, more dense. So both things are getting influenced by the same temperature, meaning that the ratio between them remains the same. And that ratio is dynamic over static pressure. And you'll essentially take an airspeed reading like this, compare it through some clever mechanism to the static pressure, and get a reading on a dial, usually like a drum dial with the numbers rotating towards you or away from you, that kind of thing. Or in a air data computer, you've got all the information you need. So it's just a bit of software to do a quick calculation and do the dynamic pressure over the static pressure and give you a value that is displayed on your primary flight display.